The area forecast for the next 24 hours.
Hello, very good morning to you and welcome to the Sixties.
Our planet is filled with signals invisible to the naked eye.
1, 0.
But space itself can be just as noisy. This is Cambridge University's Radio Telescope Observatory. It's used to examine the far reaches of space, to answer questions about the very origin of our universe.
These magnificent dishes are detecting signals from radiation left over from the Big Bang. But they're not optical telescopes in the sense of looking through an eyepiece and seeing a planet or a star. These dishes are detecting radio waves.
These telescopes allow us to see the unseen. Extraordinary images like these are made possible thanks to radio waves, microwaves, and gamma rays.
The thing is, all these waves are connected. They're all different types of something we call electromagnetic radiation. Visible light, the light that you and I can see, is just a tiny portion of this broader spectrum of waves. And we use waves to probe the outer reaches of our universe. But we use them for so much more.
In fact, electromagnetic waves are at the heart of modern technology. We use them every day in everything from medicine to communications.
That's a man's face. There it is. There it is.
Our mastery of these waves was made possible when one man published a set of equations in 1865. A man called James Clerk Maxwell.
His name's barely known to the public, and yet he's probably the finest scientist Scotland's ever produced. And 150 years after his greatest discovery, I'm setting out to explore the story of the man and his work. Excuse me, can I ask you a question? Do you recognise this person? No? Do you know who he is?
Alexander Graham Bell?
No idea.
He looks like a banker, an economist maybe.
James Clerk Maxwell. Still no idea?
Still no idea.
James Clerk Maxwell.
Never heard of him.
Albert Einstein or something. No.
You're so close! James Clerk Maxwell. Name ring a bell?
Maxwell's equations.
Maxwell's equations.
I don't know what they're about, but I've heard of them.
Right, you do physics?
I do physics.
Okay, James Clerk Maxwell, and this is your test.
I just failed physics.
That's a statue.
Is
It's a
it
statue.
actually?
That's a statue. Oh, you probably pass that quite regularly.
Quite
do you?
regularly, so it's quite an embarrassment to say.
No, but no one. I've been asking everyone here. James Clerk Maxwell. No one knows who he is. Any ideas? This is a statue of James Clerk Maxwell. And yet virtually no one around here knows who he is. But I don't blame them, because Maxwell seems to have slipped through the cracks of history, at least as far as the public's concerned. So who was he?
James Clerk Maxwell was a 19th century Scottish scientist. He used his genius to work across a wide range of subjects. Astronomy, physiology, colour, optics, thermodynamics, electricity and magnetism. He touched on all of these and changed many of them beyond recognition. He caused a revolution in physics and gave his laws for one of the four fundamental forces of the universe. Einstein kept a picture of Maxwell on the wall of his study and once said, "I stand on the shoulders of James Clerk Maxwell." It's a sentiment shared by many physicists today.
Maxwell did for electricity and magnetism what Isaac Newton did for gravity.
He's one of my great heroes. He's one of the greatest scientists we're ever going to encounter. He's on the par with Einstein, with Newton, with Archimedes. He transformed our way in which we understand the world.
He's probably the greatest scientist Scotland's ever produced. And we're still living in the shadow of his achievements, and yet no one knows who he is. Even me, a Scot and a scientist, just got this vague notion of what he did. But I want to change that. I want to rediscover James Clerk Maxwell.
Born in Edinburgh in 1831, Maxwell was the only child in a landowning family from Galloway. The scientific revolution of the previous centuries was changing our view of the world, but modern science was still in its infancy. The 19th century would see groundbreaking discoveries, and Maxwell would be at the heart of it, compelled by a probing mind. His inquisitive nature was obvious, even in childhood. When he was a boy, the zoetrope was a new invention, and the young Maxwell loved them. It's kind of hypnotic. In a sense, these are the forerunners of movies and television, and you can imagine kids in the 19th century just being mesmerised by them. Most of them would have been happy just to sit back and enjoy the show, but Maxwell wanted to know how they worked. The moving figures are a trick of the eye. Stop the drums spinning, and you can see the simple sketches that help create the moving image. This simple illusion captivated Maxwell. As a child, he would build his own zoetrope strips to entertain his family and to understand how they worked. This desire to understand the world around him continued into adulthood. Aged just 14, he produced a paper on geometric shapes that showed such mathematical ingenuity it was published, and then read at the Royal Society of Edinburgh by an established professor, as James was deemed too young. As a teenager, he conducted homemade experiments into light and colour. And by the time he arrived at Cambridge University, aged 19, he'd already published 3 mathematical papers. From the age of 14, Maxwell had been using mathematics to explain how the world worked. It was a talent he would rely on for many of his discoveries, and it was key to establishing his scientific reputation. Because while still in his 20s, he used maths to solve a riddle that had puzzled scientists for centuries. Saturn's rings, a vivid band surrounding one of our solar system's giant planets. We've become accustomed to their beauty. But in previous centuries, they were an enigma. Galileo first drew them in 1610, and they immediately fascinated astronomers. Sometimes the rings were hidden, at other times clearly visible in the night sky. By the mid-19th century, we knew the rings were composed of at least 2 vast concentric circles, over 250,000 kilometres in diameter. But what were the rings made of? And why did they stay in place?
In 1855, the Cambridge College published an open competition to answer those very questions. But the answer would have to be accompanied by a full mathematical proof. Maxwell's response would earn him his stripes as one of Britain's top physicists.
There were 3 possible explanations for Saturn's rings. One possibility was that the rings were solid rock or ice. Another that they were entirely fluid. A third explanation said the rings were made up of lots of individual particles that circled Saturn. As the rings were over 1 billion kilometres away, proving which explanation was right seemed impossible.
So how did Maxwell go about kind of disentangling those options?
Well, with great difficulty, but of course what's really striking, what's very impressive, is that he did it using pure maths. And you wouldn't perhaps instantly think that this was a problem you could tackle that way. You think, well, the way to do it is to just build a big telescope and have a look. But the mathematics that Maxwell brought to bear on this allowed him to look at these 3 cases and to basically decide which one of them was the correct answer. So if we take, first of all, the case of a completely solid ring, there's a particular mathematical equation that describes that case. The distance from the centre of the planet to the centre of the rings, that's this big R here. And I just perturb it a little bit if I disturb it.
The maths is incredibly complicated, and as a geologist, I'm a bit out of my depth. But I understand the basic point. Maxwell reduced the physical world to mathematical symbols, and then used maths to predict what was happening around Saturn. Maxwell said that a solid ring was possible, but only if most of the material was bunched together on one side of the planet.
And of course, if you look through a telescope, it doesn't look like that. So that model was discarded, back to the drawing board.
Maxwell then assumed that the rings were fluid and came up with an equation to describe how that might work.
Off he goes with his complicated mathematics.
He found that if the rings were fluid, physical forces acting on them would eventually break them up into lumps. So he discounted this possibility.
And that leaves the third possibility, which is that the rings consist of a very large number of independently moving particles, particles that are all orbiting Saturn on their own. And what he boiled all of that down to was an equation to tell you how many particles you would need in order to have the system stable. And sure enough, this seemed to work. So it wasn't just that he'd shown that the other 2 possibilities were wrong, but that this third possibility did actually work as well.
What I find staggering is just the notion that you can just use numbers to predict something you've got absolutely no knowledge about directly.
Sure. I think for me, that's almost a watershed moment in how we do physics, because it laid the foundations for really how we do physics today, because there's many examples, everything from, say, the Higgs boson to studying distant galaxies, where you can make theoretical predictions, and it might be years or decades or even centuries before you can fully test those predictions. But hey, it works. We're just zooming in on the ring plane.
Oh, that's great, isn't it?
Yeah, amazing. Here they are, right
We're
on cue.
in the ring. Look at it. What do you think Maxwell would have given to have seen this?
Oh, I'm sure he would have loved it.
Almost 130 years after Maxwell's prediction, we captured images that proved his theory beyond doubt. In 1977, an ambitious NASA launched the Voyager probe. And 3 years later, it sent home sensational images of Saturn's rings. In 2009, the Cassini probe confirmed those findings. Saturn's rings were made of millions of icy rocks. In recognition of his work, a division between the rings is known as the Maxwell Gap. But his maths has been applied beyond Saturn. This image from the Taurus constellation shows a young sun at the heart of a huge cloud of dust and rocks. As the cloud circles the star, dark bands reveal areas where rocks are clumping together to form planets. We're witnessing the birth of a solar system. And the maths we use to understand this process is the same as Maxwell's work on Saturn's rings.
Maths is a powerful tool that physicists use to understand, to predict the universe. And Maxwell was a master of it. In solving the problems of Saturn's rings, Maxwell had put a marker down. He wanted the scientific establishment to take him seriously, and they did.
When Maxwell delivered his paper, it was the only one that the Cambridge Committee received. No one else came up with an explanation. Overnight, Maxwell became known as one of Britain's great theoretical physicists. This wasn't a surprise to those who knew him, because his teenage precociousness had been followed by groundbreaking experiments as an undergraduate.
So perhaps it's no wonder that Maxwell was made professor here at Aberdeen's Marshall College at the tender age of 25. His star was on the rise.
His career may have been taking off, but this was a difficult time for Maxwell. An only child, he'd been extremely close to his parents, but his mother had died when he was 8, and just a few months before Maxwell arrived in Aberdeen, he lost his father. Maxwell expressed his grief in a letter to a friend, but the passage gives a revealing insight into his humanity and the deep feelings he had for family and friends.
Either be a machine and see nothing but phenomena, or else try and be a man, feeling your life interwoven, as it is, with many others, and strengthened by them, whether in life or death.
Maxwell's move to Aberdeen meant he was far from friends, and amongst colleagues twice his age. He threw himself into his work. Whether it was his industry or his solitude, Maxwell came to the attention of the college principal, Reverend Daniel Dewar. Dewar befriended his new professor, and Maxwell became a regular visitor for dinner, which is how he met the principal's daughter, Catherine. Maxwell's relationship with Catherine reveals the character of the man beyond his scientific genius. Deeply affectionate, he had a lively sense of humour and a passion for poetry. As their relationship blossomed, Maxwell plucked up the courage to ask Catherine to share their lives together, and his marriage proposal included a poem.
Will you come along with me on the fresh spring tide, my comforter to be through the world so wide, and the life that we shall lead on the fresh spring tide will make you mine indeed, though the world's so wide. No stranger's blame or praise will turn us from our ways that brought us happy days on a rain-burned side.
Maxwell married Catherine in 1858, and throughout their lives they remained devoted to each other. She would be a valued assistant in many of his future experiments, and he even became a willing guinea pig for one of his great obsessions. Strange as it may seem, in Maxwell's time, we didn't really know what colour was, or why we saw colour at all. In the 17th century, Isaac Newton had given us food for thought. By using a prism, he had split sunlight into separate colours, the familiar colours of the rainbow. He showed that what we perceive as white light is actually a mixture of different colours. Newton said that every colour we see was a result of mixing the colours we see in the rainbow. He tried and failed to establish the rules of mixing. 150 years later, we weren't much wiser. Maxwell was interested in colour and why we perceive it throughout his life. And his first real breakthrough came as a Cambridge student. Artists seem to be ahead of scientists on this. For centuries they had been creating a vast palette of colours, often by just mixing red, blue and yellow. Artists refer to these three as the primary colours, and using them they could create entirely different colours.
So if a painter was mixing red and yellow, he would get orange. And if he was mixing blue and red, then he'd get purple. But if they were mixing blue and yellow, then they would get green.
As a student, Maxwell read about the work of Thomas Young. Young thought that there was something significant about the number of primary colours. But he also thought biology had a role to play.
Young argued that the human eye had 3 receptors in it, each one sensitive to a particular colour. He argued that the brain worked like a painter, combining messages from each receptor to build up this perception of colour. It's a stroke of intuitive genius. We just didn't have any proof.
Young thought that these receptors corresponded to the painter's primary colours. Taken by Young's 3-colour theory, Maxwell wanted to test it. He devised a way to mix the primary colours with mathematical precision. He then tested those mixtures on a wide range of people to see if they all perceived the same colour. And he did this with a deceptively simple tool.
So this looks old. What's this then?
This is Maxwell's original colour wheel, which we are very pleased to have in the laboratory.
So that's the original thing.
This
that's what
is
he made,
the original thing. That's it. It's slightly beaten up. It's been used a lot, and that's because Maxwell used this to test out the mixing of lights among all his friends when he was here in Trinity College. It is pretty antique, as you can see, but the idea is you put different amounts of the coloured papers here, and then when you rotate them, then they mix up. And this works because of the typical time that the eye can respond is a 20th of a second. And so if it goes faster, the eye will interpret this as the mixture of the colours.
And this is a motorised version, is it?
This is a motorised version of it, and we can actually demonstrate how the colour mixing works with this rather pretty demonstration here. We were going to mix red and blue. We'll rotate it rapidly, and then we will see which colour we produce.
Just like his childhood zoetrope, Maxwell's colour wheel would spin so fast it would trick the human eye.
So if you were going to bring up that light...
This one here?
That's right.
Instead of moving figures, he'd be mixing colours just as artists did, but with mathematical precision. When he mixed red and blue, he got the same colour artists did when they mixed paint.
And that's kind of magenta, purple.
Yes, it's a sort of a magenta colour.
If Young was right, and there were receptors in our eye that responded to the artist's primary colours, then perhaps mixing red, yellow and blue in equal measure would produce white. But it didn't. So Maxwell tried different combinations.
We can begin now to reveal green as well as blue here. And if we just do a little bit of fiddling around with these discs, we'll be able to get equal amounts of red, green and blue, and we can then see what colours we observe. Okay?
So it's white. I mean,
it's white.
It's the only colour you call that, white.
So this is a beautiful demonstration of the fact that the primary lights, and notice the word light, not pigments, the primary lights are red, blue and green. And you can create any colour of light by suitable mixture of different proportions of these. What happens in paintings, pigments absorb light, whereas this is emitting light. So the upshot of all of this was that Maxwell was able to produce a rather beautiful colour triangle diagram, which could indicate how you would create any colour by mixing the 3 primary colours.
Maxwell's colour triangle allowed him to pick a specific colour and work out how much of each primary colour would be needed to reproduce it. This was made possible by his mathematical precision and systematic testing. Maxwell's work swept aside a sea of confusion. He vindicated Young's theory and demonstrated that we see colours in paints differently to the way we see colours in light. He established the primary colours for light as red, blue and green. He realised the receptors in our eyes were sensitive to those 3. And that by mixing them, we perceive the vast range of colours. A few years later, he provided a stunning display that he was right. In 1861, Maxwell was invited to the Royal Institution in London to give a lecture on colour vision. But he didn't want to just talk about the principles. He wanted to demonstrate them to his audience. What he did would astonish them.
Maxwell took 3 photographs of the same object. Each photo had a different filter on it. One was red, one was green, and one was blue. That gave Maxwell 3 photographic plates that he could use to project an image with.
When Maxwell projected the image from the red photograph onto the wall, he got a red picture. In an age when photography was black and white, this was interesting, but hardly revolutionary.
But if you project all 3 images onto the wall at the exact same spot, something special happens.
The audience were looking at the world's first colour photograph. They were stunned. Maxwell had chosen the perfect subject for his picture, a brightly coloured tartan ribbon. By layering red, green and blue images on top of each other, Maxwell established the possibility of creating colour photographs. 150 years later, we use this method daily because this 3-colour principle is used in colour TV, computer screens, even mobile phones. The colours we see on our screens, however big or small, are created by carefully mixing the primary